Good afternoon, everyone. Sunil Kumar, one of the research scholars in the Department of Computer Science at IIT Guwahati. I'm pursuing my PhD under the supervision of Professor Arjit Sur and Dr. Rasmita Barua. Today we'll have a brief discussion about the unsupervised method to train a deep learning model, which is called the self-supervised learning. So, before going into the detail, So before going into the detail, we need to address a very fundamental question here. Since it's a learning method, we need to know what is learning. So can any one of you suggest some definition for the learning? So in the general sense, it is a process of acquiring knowledge, skills, behaviors, or understanding through the experience, study, or being taught. So the point what I want to make it here, that the learning can be happened with experience or being taught. It could be in the supervision or without the supervision. So what do I mean by supervision? So you can remind our childhood, when we were like very naive, we had a teacher or tutor to guide our learning process, because we had no extra previous experience with the learning, right? With the content we are about to learn. So we had a tutor or a teacher which basically was guiding our learning process, right? It's telling us whether we are wrong and whether we are right. And another way of learning of a human is without the supervision. It is also called self-learning kind of thing. So sometimes you don't have a supervisor or a guide or some tutor to guide your learning process. We only have given the contents and we learn with the given contents. We do the reasoning and then we got to know what we're supposed to do with these things. For example, you can take when in the childhood, somebody give you a cycle. It may happen there is no one to teach you like how to train a cycle, how to bicycle or something. So in that case, we start paddling and we do small things with the cycle, and finally we end up learning the cycle. You know how to drive it or something. So to summarize it, the learning can have two different ways. It with the supervision or it without the supervision, right? And so what is learning with the perspective of artificial intelligence? So it is a process by which an AI system improves its performance on a task. The task could be computer vision task, NLP task, or something. So on the task over time by extracting pattern or knowledge from the data, right? So in the ML model, when we talk or deep learning model, we basically give some data to the model, right? So up to which whatever you have learned, we have given data with the two basic things. So one was the feature of the data, another was the level of the data, right? So feature was input to the model, then the model predicts something, right? And there was a level to tell whether the prediction is right or wrong, right? So how this learning with the deep model happens into the supervised scenario. So we have a data, we fed this data to the model, right? So this data in the forward pass, this data, the model processes this data, right? And then give us some predictions. So this is the image data set. So we will have a prediction in the size of 9 vector size, right? Because there will be 9 class at the end, right? So it will give a probability vector of 9 class, and then this probability vector will be compared with the ground truth vector, right? So ground truth probability will have one where this 7 belongs to the class and others have a 0. Then error term will be calculated, right? And in the backward pass, this error term go to the model, and this model basically adjust its weight so that in the future epochs its performance can be improved, right? So the important things to note here that this ground truth acts as a supervision here. So is it possible to train this model without this ground truth? No, not possible, because if the ground truths are not available, this error term won't be calculated, right? And since we are not able to calculate the error term, no backward pass will happen, right? So these ground truths are very important for the training of the model. So what we can conclude from this slide, that the deep learning model needs some kind of supervision for the efficient training, right? Without the supervision, this type of training is impossible. Okay. So coming to the next slide, we will try to understand more about this supervision. So are you familiar with the image classification task? So the image classification task is basically we are given a data set where the features and labels are available, right? So basically images and their labels. The labels tells whether the object in the image is a dog or whether it's a bird or whether it's a cat, right? So these labels, dog, bird, or cat, acts as a supervisor in the image classification task. Another task would be semantic segmentation, right? So in the semantic segmentation, what we do, we try to segment a specific part of the image where any objects are available or not, right? So in that case, we have a segmentation mask. Okay. So this segmentation mask basically separate the pixels which belongs to this object and the background. So this segmentation mask acts as a supervisor to guide your model in the training process. Your model can predict some kind of segmentation mask. Then the error can be calculated and this error can be sent backward in the backward pass. So okay. So tell whether the prediction is right or wrong and whether the model need to adjust its weight or not, right? So if you have a model and if you have enough number of labels data set, the supervised learning works really well. Okay, so now you have vision transformer and a resonate and a large data set like ImageNet or kinetic data set. So this large size of data set can have a very good performance given a very large amount of label data set. Okay, so but there are several challenges while collecting this large size of data set. As you can see in the plot, these are some data set, and one of the data set, ImageNet and Kinetics, have a millions of images in it. So you can consider the amount of time given to annotate or label each data, because someone have to sit down and annotate each image in the data set, right? So that it can give it to the model. And if there is a millions of image, you can think about the time it takes and the cost which is involved with it. And not only that, you also need a human expertise. You cannot give it to anyone and can tell them to, okay, label the data set. Because sometimes in the image, there are multiple objects are available and you need to decide whether which object need to be considered because there will be only one label assigned to the data or image, right? So the basic conclusion is here, collecting and labeling this huge amount of data set is very hectic and challenging task, right? So even if let's say you are managing to collect the data set and label it, what happens in the supervised learning? We train a model for a specific task. It could be only classification, it could be segmentation, it could be object localization, it could be object discovery. So whenever we train for one time, it is trained for one specific task. Okay. So what if you want to use this model for another task? Is it going to work? Can you use a classification model for segmentation task? No. So this kind of training in supervised learning is very task specific training. So even if you somehow manage to collect the data and label it, so if you deploy this model for the other kind of task, so it is going to give a very poor performance. And not only that, let's say I collect image from the outside world and I train my model. Then I try to classify the fish images, which is taken from the underwater. Whether it's going to work? No, because it is trained on the outside data set. It does not have any knowledge of the data set is coming from the underwater scenario, right? So these kind of supervised training are very task specific. And it does not work well when it is given to the other task or into the data collected from the other domain. So to conclude this slide, we can say that the supervised learning is a bottleneck for building more intelligent or generalized system. What do I mean by generalized system? It's like you train once and you can use it for different tasks. So the generalizability somehow is very less in the supervised learning scenario, right? So it cannot do good with the multiple tasks, acquiring new skills without massive amount of label data set. So unless you have a very large size of massive large size of label data set, you cannot train a vision transformer VIT, right? In the supervised scenario. So one of the feasible solution to deal with this problem is learning with the unlabeled data set. What do I mean by the unlabeled data set? Learning without the labels. We have only images. We don't know whether it's a dog or cat or whatever inside the image. We only have a huge amount of images. And you can think about collecting these images is easy because you can connect it from the internet source, right? You don't need to label it. You don't need any domain expertise. You can simply collect the huge amount of images and you can use it for the training, right? So going for the unsupervised learning can be a better alternative for the supervised training. So this task is very similar to giving a deck of cards to a child, 2-3 years of a child. In each card there is a image of animals, different animals, and you tell that him or her to you group this deck of card into the different clusters. So since 2-3 years child does not know all the animals, right? So what they will do, how they will cluster these cards? Any idea? Yeah, so it will go for the property of the animals, right? Color of the animal, appearance of the animal, size of the animal. Based on that, he or she will be grouping all the cards, right? So the important things to note here that when we don't have a supervision, what do? We learn with the property of the data set given to us, right? We reasoning with the whatever the data we have. So the learning with the property of the data is called unsupervised learning because there is no supervision. So whatever we learn, it could be more generalized, right? So if I teach a child just with the labels, this is cat, this is dog, it will simply skip other kind of knowledge. It will just learn something like, okay, dog have this, cat have this. But if I give him a deck of cards and tell him to group it, it could have a different kind of knowledge. It could have learned different property of the data set, right? So the unsupervised learning give us a freedom, give a model to freedom to learn hidden knowledge inside the data set, right? So before going to the deep learning, I will give you an example of unsupervised learning in an ML scenario, machine learning scenario. So any guess which algorithm I'm going to talk about in the unsupervised learning for the clustering? K-means clustering, right? Very famous. Okay. So what does K-means clustering basically do? It also group the data based on their feature similarity, right? And what do you mean by the feature here? The feature is size, color, appearance, something like that, right? Somebody is sitting there and writing these features for each images because it is the ML scenario. There is no deep learning involved, right? So it need feature which is extracted by the human. And when you go for the deep learning, you don't need these features, right? You only give image to the model. And with the machine learning, you give feature to the model, right? There is a big difference between the machine learning and the deep learning things, right? So deep learning like reduce this overhead to write the features, okay? So use a CNN model which extract the features for you, right? Instead of writing all the features for the images, right? So the point is that it iteratively cluster the data based on their similarity, based on the feature similarity. But the point is that it's not a learning method, right? It's rather an iterative process. Okay. So what if we go for the learning process? What if we go the DL process? How are we going to train our model with the unlabeled data set? Okay. So we already know the deep learning model needs some kind of supervision. So in the unsupervised setting, there are no labels, right? So if there are no labels, no supervision, and if there are no supervision, how are you going to calculate the error and send it back to the model? And your model will adjust away. Okay, so the question remains same that how to train a deep learning model with the unlabeled data set. We have only given the unlabeled data set and the deep learning model, right? And the task is to train this model. It's a CNN, let's consider it's a CNN model because we have an image data set, right? How can we train this model like a child to learn a hidden knowledge within the data set without giving any labels, right? So to deal with this problem, a new way of training a deep learning model in unsupervised way came, which is called the self-supervised learning. It improvised the idea of training a model by just using the property of the data set like a child. I already given the example, right? So in the fancy term, you can say that it generates the supervisory signal from the unlabeled data set itself. Okay, and these supervisory signals are one of the properties of the unlabeled data set. Like we have already discussed, size, color, and appearance, something like that. It could be advanced in this scenario. Okay, so also we can say that it uses the inductive bias to guide the learning process. And what are the inductive bias here? It is the assumption of prior knowledge about the unlabeled data set. It could be color, rotation, spatial or temporal information. Okay, so we will discuss this later, don't worry right now. Okay, so we will try to understand this process of generating signals from the data with an example task which is called grayscale colorization. This is one of the naive example of a self-supervised training, and it is my first learning also. I have first gone through this paper only. So we will try to understand this task, and after knowing this task, you will understand how we can train a model by using the property of the data set. How can we calculate the error term and send it back to the model, right? Forward and backward pass. So before going to the grayscale colorization, we need to revise our problem statement here. So what is our problem statement in self-supervised learning? We have given an unlabeled data set and a model, deep learning model, consider CNN here. And the aim is to learn the meaningful feature representation without labels. So what is the feature representation here? Again? Yeah. So feature representation of a data set is basically a vector form of the data set. So you have a CNN, right? You give an image to the CNN, then CNN give you a feature, you extract the feature, and then this feature is flattened and given back to the fully connected layer. You remember from the last day? So before the fully connected layer, whatever the representation of the data set you get, that is called the feature representation data set. So basically, instead of using the image, we use this feature representation. And if your training is very good in the CNN, the feature representation of image will capture the essential feature property and characteristics of the input images. So if your model is very good, the two different image of O have almost similar features, right? And that image of 7 and 2 have a different features in the vector spaces, right? So feature representation is basically a vector, one-dimensional vector, which represents the image, okay, and extracted from the deep learning model, or you can say CNN if your image is the input, right? Okay. So now we know our problem statement. We'll try to understand how we're going to solve it with the grayscale colorization problem. Okay. So we have given an unlabeled data set, right? There is no label is available. So can we get a grayscale image of this color image? Yes, there are many image processing. Pardon me, the spelling mistake is there. So there are many image processing algorithms are available, which you can simply provide a grayscale image. You can write a simple 5 or 6 line of code and give the big data set, and it can convert the color image into the grayscale image, right? So now we have a color image and their corresponding grayscale. Okay. Now how are we going to use this thing to train our model? Into the next step, we can give the grayscale image to our model, and I can tell my model to color this image. So can you color this image? Can you find out the color into the grayscale images here? So in the simpler term, this grayscale acts as an input to the data model, right? And this color image acts as the labels, as a supervisor. So our model will predict some color image right here. Then this color image will be compared with the actual color image. Okay, so we can have a loss function here which can differentiate between the predicted color image and the actual color images. And whatever the error term, we can back propagate it into our network, right? So in this way, we can train our model to learn something about the data set, about the semantic information present in our data set. So now you see how we have only unlabeled data set and we have a deep learning model, computer CNN, and somehow we managed to train this model, right? So similarly, so now we can define, okay, so the task like grayscale colorization, which is used for self-supervised training, is called pretext task. Okay, we call it a pretext task. So there could be a multiple variety of pretext tasks. So can anyone tell me one of the pretext tasks? Just think about it. Like image colorization. Can you think about any other? You already know, you have already done it.
Sharpening.
Sorry?
Image sharpening.
Yeah, image shuffle could be, like not image shuffle, but basically what you are trying to say, we can break the image into the different patches, right? And then we can shuffle the patch into the image. You already solved it as a child, right? Then I can tell my model, can you arrange it into the relatively right position? So if we do this task, our model will learn something about the image, right? And another task would be rotation. I can have an image and I can rotate the image with certain degree, right? Then I can tell my model, can you predict the actual rotation of the image? So if I turn my image by 90 degree, then my model should predict 90 degree, right? And I know it's a 90 degree, then I can calculate the error term and I can send it back, right? So another thing, do you know the video? Videos are basically a set of frames of images, right? So these images move very fast. So video is nothing but a set of image frames. So there one frame should appear after the frames, consecutive frames. We can shuffle the order of the frame also, right? And then give it to the model, and I can tell my model, can you predict the right order of these frames? Okay. So here we are using temporal information, and here we are using spatial information, right? So here temporal information is used to predict the video frames, right? Another one of the most widely used and successful pretext task is contrastive learning. Okay, this task came in the beginning, and at last this came the contrastive learning, which is widely used and most successful. Why it is very successful, we'll see. So the contrastive learning, basically, there is no labels available, right? So what it do, it take an image and generate the multiple image augmentations. How do we generate the augmentation of an image? by applying some geometrical or photometric transformation over it. What do you mean by a photometric transformation? Cropping. Sorry, photometric is color jittering, gray scaling. You're playing with the image color, hues, And what do you mean by geometric transformation? Cropping it.
Scaling.
Yeah, scaling it. Yeah, cropping it or rotating it. Such kind of. Okay. So it generates the multiple augmentation of the image. And our model, if it is learning well, it should give the same representation for all this augmentation and this image, right? Because they are the part of the same image, right? So it trained the model to bring the feature representation of all the augmentation of an image closer into the vector space. And it tells that if image are from the two different image, the augmentation are from two different images, then it should be placed apart into the vector space. So this type of loss we call the contrastive loss. Okay, you know the big model? Do you know? Self-supervised model, anyone know? You know Cliff? So these are some self-supervised model. There is a DALI, I think you know, right? Art generation. So they are somehow using all these things, right? You don't know. Basically, these things are happening because these models are very large in size and collecting data. Recently you heard about the ChatGPT. It is taking all the data from the internet. So is it possible to level all the data? No. So they are using the self-supervised training to train the model. Okay, you cannot level all the data, right? So this contrastive learning is working very well because it learns something about the image, semantic information. Because it compares the image. Okay, instead of doing some photometric or geometric task which you have seen before, colorization, color patch predictions, frame predictions, right? Okay. So one question I expect from you here, right, that you can ask. You have talked about the many pretext tasks here, but none of the pretext tasks seem to perform any actual downstream task like image classification, segmentation, object discovery. None of them are performing something like that, right? So how we are going to use this pretext task or this self-supervised learning to do such kind of task, image classification, segmentation, or object discovery, object localization, name it. Okay. So this thing is done by the transfer learning approach. So what is this transfer learning approach? So for now, I'm dividing this self-supervised learning in two steps. So first step is pretext task learning. So here pretext task training is happening, right? And next I am placing this downstream task. So downstream task could be image classification, clustering, semantic segmentation, object localization. So anyone can define transfer learning here? So transfer learning is basically a learning technique where we train a model for a different task and then transfer this knowledge to the different task, okay, to perform other tasks. So how do we transfer this knowledge? We use this pre-trained model, right? We use this pre-trained model. Instead of initializing the model from the randomly initializing in the other task, we initialize with this weight, right? So we take the part of the model, we take the CNN from here, okay, which is already trained, and put it in our new model as it is.
Just we are taking only the model to switch to the other model.
Yes. So we are taking the weights from here to here, and it could be just the part of the model, okay. So such kind of learning is called transfer learning, like we are transferring knowledge from one part to the other part. So what is the benefit of self-supervised learning here?
Computation.
Yeah, so first thing is there, if you want to do some task specific training in supervised learning, use data set labeled, right? But here we can do this use training in the first part with the unlabeled data set. And then even if we have a very small size of data set which is labeled, we can use the data set to fine tune the other part. But you understand the benefit here? So even if, let's say, you're working in a civil or mechanical or medical imaging, it's not possible easy to get this all data set and label it, right? But you can label a small part of the data set. And your model already know a lot of things about the image. Then you can give this small data set which is labeled and you can fine tune this model. Okay? Got it? So, going to the next. Okay. So now we'll try to understand this whole scenario with two examples: image clustering and image classification. What is the difference? Yeah.
Means in first case, when we were unlabeled data, first we are finding the classes, and after that once we are able to find the classes, when we are coming to the self-supervised learning?
No. Let me explain this. Maybe it will be clear to you. This is the same thing. Okay. So what is the difference between image clustering and image classification?
Image clustering is just with respect to the same type of images clustered at a one means aggregating it in one neighborhood.
Yeah. And classification, we already know the labels,
Yeah.
so we fine tune it, right? So we train the models. Okay. So how can we use this pretext? So now for once consider we already done the pretext task phase. We have the trained model. Okay. So how can we use this pre-trained model for image clustering? So what we can do, we can use this self-supervised trained model, which is not visible here because of the color composition. Okay. So let's consider this is the pre-trained model, which is the pretext task, which is trained with using the pretext task. So we can give our image to this pre-trained model, and it can give us the feature vectors, right? I already told you what is feature representation and vectors. Then you know the k-means clustering, which works really well with the feature vector. And if your model, if your training is very successful in the pretext task phase, so the feature vector should capture all the essential information of the image, right? It should be very informative. Now you can apply some kind of k-means clustering over it to find out or group the labels, group all the feature feature vectors. Now the level of feature vectors can be replicated back to the image. Okay. So this way we can do the image clustering. So instead of using this image vector, we are using this feature extractor now. So the task has been very simple now. Okay. And how are we going to use for the image classification? So as I told you, we can take the pre-trained model from there, okay, and then put an extra layer over it, which we call the classification head. Okay. And now we have a small data set which is labeled, and we can use this data set to fine tune our model from here to here. And since we have a label, we can guide our training. Okay. So this way we can do the image classification. Now you understand? So
one thing, firstly we are doing clustering, or firstly we are getting converting the image into the form of vector. Which process is taking first? Is it clustering or
no? These are two different tasks.
Okay.
I'm showing as a downstream task. Okay. These are two different tasks.
Backward.
Yeah. Going back.
No. I'm saying that it is taking backward or in forward direction. Means suppose that I have a collection of images.
Yeah.
And I don't know what is it means, what type of image is there. First, to get the idea what are the classes of images, I have used the unsupervised learning and clustering.
No. Let me clear. I understood it. So basically, there are two steps, right? As I told you. First step is pretext task, and another step is downstream task. Your image clustering is a downstream task, which comes here. So first we do some kind of pretext task here. You can choose one of the pretext tasks from here, okay? You can choose any one of the pretext tasks and perform this pretext task to train your model, okay? In the first part. Now your model is trained here, right? Now you can use this pre-trained model for the next task, which is the image clustering, right? Now let's say I transfer this trained model here, right? Now I have an unlabeled data set. I can give the unlabeled data set to this model, which can give us a feature vector. And now I can apply k-means clustering over this feature vector. I hope it's clear, right?
Can you repeat this once again?
So there are two parts of the training. First is pretext task. Okay. So first is pretext task here, which is above, right? You can choose one of the pretext tasks, right? And the other part is downstream task. And downstream task could be one of them, image clustering or image classification. For now, I discuss image clustering. So what can image clustering do? It will take your images and the pre-trained model can give you a feature vector. And then later we can apply some k-means clustering over this feature vector to find out the different clusters. For image classification, you can put your pre-trained model here, then add one extra classification head here, and then have a small data set which is labeled to fine-tune this whole model, forward and backward process training. Okay, this way you can train your model for image classification. And this downstream task will be different. You can use segmentation, you can use image localization, you can object discovery and all. Okay, so moving on to the next part. So concluding the self-supervised learning, there are two parts of the learning: pretext task and downstream task. Okay. So now when we know the self-supervised learning, we will try to understand the advantage of learning with the unlabeled data set. So what are the advantages? First advantage is that collecting the unlabeled data set is very easy, right? We can collect it from any source, from internet, from anywhere, right? we can have a huge data set, and we don't have any overhead of, it removes the overhead of labeling time and the cost, right? So the labeling time and cost is gone. Another way is, let's go for the better generalization across different tasks, because we can train a model with the pretext task once, and then we can use it for different tasks with a small data set, right? And third is that it mitigates the human bias during labeling. What is the human bias during labeling?
What is
So human bias during labeling. So let's say you are expert and I give you an image to label. The image could have multiple objects in it, right? So you can choose one object which is more visible to the image, right? And give that label. We ignore that other label, right? So there is a biasness towards the labeling. So that kind of labeling bias can also be mitigated because model is not learning with the labels, right? Other thing is that I want to talk about, let's say each one of us work from the different domains, civil, mechanical, bioscience and all. So we want to use the deep learning for our work. So is it possible to collect the data all the time? No. And labeling it. So this problem can be mitigated using the self-supervised learning. Like we can simply collect the data and train. Or we can use the any other data set to pre-train our model in the self-supervised scenario. Then we can use our data, which is small data set labeled. Okay. Other thing, one of the important thing about is that there's a multi-model scenario, right? So the multi-model, what happens? We train the model with the different modality together. We use image, text, and audio together to train our model, right? So consider the supervised scenario. You have to label all these things, not only image. You have to label audio and as well as you have to label the text also. But when you go to the self-supervised scenario, you need not to label any of them. You can simply use the raw data. So self-supervised learning is the best way to train a model in the multi-model scenario. And there are a lot of available, like ChatGPT, ChatGPT is trained with the different modality of the data set. There is a Click, there is a DALI. All the good fancy models, they are using the multi-model scenario. They are using the self-supervised technique. Okay?
Sonal, sir, there is a question from online chat.
Yeah.
How to measure the clustering? Whether I have to test on external label data set?
Sorry.
How to measure the clustering? Whether I have to test on an external label data set?
Yeah. See, there is a big confusion here. Once your clustering is then done, you need to evaluate it, right? So let's say I'm a company and I'm delivering a product to you. I'm delivering a model to you. So first I need to evaluate my model, right? So while training, I need some of the label data set to evaluate, right? Once I know this model works well, I can deploy it to you. And you don't have a label, you need not to worry about it, right? So while as a researcher or as a company, when we train a model, we need to evaluate our model on some scenario, right? So we need some labels to evaluation. But using labels in the evaluation does not decide whether it's a supervised or unsupervised. Okay? I hope it's clear, right? Okay. So now coming to the real-time application of the self-supervised models. All these models, you are familiar with Gita Copilot? So Gita Copilot basically predicts the next line of your code, right? So this GitHub Copilot is also trained somehow using the self-supervised learning. Okay. This ChatGPT, already know. This is also Google Assistant, Apple ID. Apple ID used to for face detection and biometric. The Amazon Prime Air drone delivery system, and many more. DALI, Google Lens, Microsoft, even the Zoom, which you are using for document summarization. You have a Samsung iPhone S23 or 24. There is a lot of AI features are there. Document summarization and all. So these things are using all these things, right? So these are some of the real life example which we using, but we don't know these things are using this type of technology, advanced technology, right? So for the concluding the session, the self-supervised learning is the bottleneck for building more intelligent or generalized system. And self-supervised learning is taking us to the more human level thinking, right? How human used to learn. Okay, it's not always supervised, right? Most of the time we just learn with the data. Okay, next is it's bridging the gap between the unsupervised and supervised learning. How? Are you familiar with the semi-supervised learning? So semi-supervised learning lies between the unsupervised and supervised and self-supervised learning. So it uses some of the portion of the data which is labeled and the majority of the portion of the data which is not labeled together for the training. So in medical, let's say medical imaging scenario, you cannot blindly believe on the model, right? So you need to give some level of supervision to the model. So you cannot go completely self-supervised. So you have to give some portion of data in the pretext task only. So such kind of learning we call semi-supervised learning. So it is bridging the gap between the supervised and unsupervised learning. And finally, it is reshaping the machine learning for being more efficient, scalable, and adaptable. Okay. So this is all from my side. So these are some research which I am working on rightly in our lab. So this is on the semantic segmentation. This is for the classification task, and this is also for the semantic segmentation task. You can visit my GitHub to know more about my research. And if you have any question, you can ask. Any question?
Any question from offline audience?
Okay.
Do you have any question from offline?
Okay. See, if there is no question, thank you for giving me an opportunity. And,
Thank you everyone for attending the presentation. We thank Sunal also for a wonderful presentation. So next session will start from 3 p.m. It is related to the underwater vision applications. So there will